My name is Carlos Acosta. I've been in the production business since the early 90s. I started when the electronic side of everything was analog, almost exclusively, and pretty much everything was shot on film. And I, I met Dave Satin a number of years later, but he knows what I'm talking about. So it kind of interesting to go through kind of the end of the film era and ushered in the new era of digital cinema. I had a rental house, and I started that in
Carlos,
about
turn
19.
around.
Hang on a second.
There he is.
Well, I don't have a monitor. Is this too close? It's like the electro boom guy. If anybody watches Electro Boom, you get bonus points today. There, we'll put this here. Anyway, so I had a rental house that was in Texas, and I rented cameras, lights, and audio, and we had both film and digital stuff. But I pretty quickly got rid of all the film stuff and started doing just digital only, and it was it's been a giant experiment ever since. And it had some personal challenges towards the end of that. I ended up selling that company and getting out of rentals altogether, and I just wanted to make stuff at that point. So, roughly 2006, I kind of dusted off my electrical engineering training and mechanical engineering training, and just started a small manufacturing boutique companies. So I've made some products that are kind of out in the wild. The Scatterbox 2 is one that some of you guys have heard of, but most of what I've designed and made is commercial, industrial, one-off prototypes, a lot of research type stuff. So those aren't things that hit the general market, but that's where a lot of my experience is. So today my daily work is mechanical and electrical engineering and software development for all of those pieces and parts. So I design the electronics and all the software that goes with them, and quite a bit of experience in power electronics, which I suspect is why Jamie wanted me to focus on this particular topic. So I spent quite a few years as a DIT when DITs were called video engineers, and although, just to be completely fair, my last day on set was, I think it's like 2007 or 2008. That was like when the Alexa was a brand new camera. Was my last official paid day as a DIT on set. So I haven't forgotten exactly what the basics are, but things have changed quite a bit since 2008. Some of you guys might not even have started until after 2008. So I'm not an old man yet, but I'm getting there. So anyway, starting with the basics. Jamie, is there anything that you wanted to do to kind of introduce the agenda, or just kind of roll with it?
Here, I got you. One second. So, hey, everybody, here's what we got going on. These were topics that people had posted on DIT WIT and showed interest in. And it's going to be a very basic class. It will definitely get into some deeper things, but there was somebody that wanted to know how to build their own power supply, and we're not going to cover something like that today. There are solutions that already exist for that kind of thing, but we want to kind of go over the basics and talk about all the things that you should know when it comes to building your own 12-volt system, cables, polarity, etc. You can see the agenda here. If you have any questions, if you don't mind, try and digitally raise your hand using the participants panel in the bottom right corner. It says raise hand. And then after you ask your question, just lower your hand and I'll keep an eye on that. And if you're shy, you can always message me privately and I'll ask your question for you. Carlos is a wealth of information, so throw him some curveballs. I bet you cannot stump him. So with that being said, let's start with the basics, Carlos.
All right. So the basics. It's always hard to know where to start. on any complex topic for me. So I'm just going to take a kind of a stab at it. Everybody's probably at a somewhat of a different level. You know, I can see Melissa right now. She's like making her own cable, so clearly she's not starting at level 0, which is great. But I think one of the goals of this presentation is to convince everybody to try it, at least. All of you out there are in a technical profession, and you're being bombarded with technology every day, and a lot of that is finished technology, but it's not necessarily stuff that is intended to go together. So most of you have probably at some point faced, like, I want to interface thing X to thing Y, but I don't know how to connect those things, or I want to power it in a way that the original manufacturer didn't intend this stuff to be connected. You know, a lot of you know, what you use, routers and all of these other you know, monitors and all those kinds of things, for the most part, are designed to be in a studio somewhere. They're designed to be in a fixed installation. Yet you're on a beach somewhere getting rained on in the middle of the night, and like, oh man, this doesn't work, or you know, this thing broke. So I'm hoping to hoping that I can answer some of the questions about how to you know, best survive some of these things, and but trying not to be overly technical on any of this stuff, if that makes sense. So let's see, what are the basics? If it's kind of skipping ahead, you see that, you know, the calculating your amps, that's kind of an interesting one, but the basics are, let's see, and forgive me for some of the ad lib. I didn't really prepare a ton for this, but the basics are, we're trying to move electricity from point A to point B. That's not just power, that's also signals. And I think perhaps a misconception from some people is that it either works or it doesn't in our digital world. And in reality, um, everything is analog in our entire world. You can't just like flip something on. A lot of people will say, well, how much, you know, how many amps does my monitor draw? How many amps does my camera draw? How many, you know, those kinds of questions. Well, the right answer is, it's constantly changing. And I may be able to demonstrate that a little bit later, but it's always, everything is always changing. And even if you look at something as simple as a wire has a whole lot of electrical properties that that beyond, I guess, let me see if I can say this in an easy way. Most people understand that wires have some sort of electrical resistance that go through there, but wires are also inductors, which means they create a magnetic field around them, and that causes its own issues. Wires even have capacitance, which cause issues. That's especially on the signal side. So a lot of this stuff we're not going to cover in enormous detail, but I think that probably the thing to start with is, there is no end to most of this discussion. I think for any design engineer that's been doing it for a long time, they've already decided that there's no way they're ever going to know everything. They're not going to learn everything, and that includes me. I don't know everything, and as much as I try to learn stuff every day, I'm not going to learn everything before the day I go to my grave. So we'll try to cover the things that make sense for DITs, for on-set work, and all those kinds of things. Jamie's going to try to keep me from going down rabbit holes and talking about things that make no sense to anybody, or they don't benefit anybody now. And I'm hoping that as we discuss things and we identify a rabbit hole, perhaps, that we can take some notes on that and create isolated classes, that this can blossom into a 3, 4, 5 part class down the road that focuses on specific things about, like, digital signaling over B and C cables. You know, how do you get signals from point A to point B? That's a whole topic on its own. So you know, examples like that. So shall we move on to point number 2, or unless anybody has any immediate questions?
Yeah, if anybody has questions about like the basics of just how to get started, or how to wrap your head around planning, or or whatnot. Though, I mean, I guess the goal here for everyone is to either build like a mobile setup that's 12 volt or 24 volt or 12 volt, or start to, switch their main DIT card over to 12 volt or 24 volt so that everything video at least can be DC powered. And then maybe once that's good, you start to move into the data side of things.
Right.
Do you want to go over maybe some beginner toolkits for those who don't have them, like a basic, like just like if you're starting at the basics, like, okay, these are the tools you're going to potentially need before really getting into it.
Yeah, that's actually a pretty good idea. I'm going to move the camera over here, and I'll pull out some of the usual suspects. So let's see, I can kind of introduce you to kind of this is kind of a work environment that you would expect, for somebody who's designing electronics. But for the very basics, for on set, what I carried for years and years and years is kind of a basic soldering station, which is something like this. This is a Weller WS51, super common. They've been around forever. It's it's cheap, it's modest performance. For the most part, once you get lower end than that, they get increasingly difficult to use. So if you're like, hey, I got this $20, Banggood thing or whatever, that's like a single pencil, usually those things have so many problems with thermal recovery and some other issues related to soldering that it's just not worth it. So this one's about $100, and if you were just doing really big wires, you can get away with the cheaper, crappier soldering irons. Almost everybody in this audience is going to be dealing at some point with stuff that's relatively small, maybe a LEMO connector or something like that, and a reasonable soldering iron is kind of critical to that. So if you think that $100 is too expensive, think about the frustration that it saves in my mind, because you could buy 50 of the $10, $20, $30 soldering irons, and they're not going to equal something that's decent. For those of you who are a little bit more brave, a soldering station like this is made by a company called JBC, and the benefit of one of these is there are a million different kinds of tip shapes that cover just about every imaginable scenario, from tiny connectors to big connectors and all that kind of stuff. But this one ends up costing about $500, and it's a little bit less portable than the other one. It's a little bit heavier and all that kind of stuff. So this is nice if you're doing a whole lot of that stuff. Not necessary to spend $500. $100 is probably safe enough. And the next thing is just wire processing tools, like these guys. And I'm, all the usual stuff. I got, for me, I get the highest possible quality diagonal cutters I can possibly get. These particular ones are made by Exolite. They're like $20 or $25 a piece. And they make a huge difference when you're working with small wires. The kind of coarse, the cheaper ones that you can get from Home Depot or whatever are fine if you're working with big wires. But as the wires and as the project gets smaller and smaller, the better tools are required. And I've spent a whole lot of time on set in some difficult location, and it's cold and it's raining and all that other stuff in the middle of the night, stress trying to fix something so that we can get the next shot going. And that's the last. I don't want to be messing around with my tools, so I'm pretty aggressive about buying the right tools, and then they last forever. Let's see, wires. Yeah, go ahead.
I've got these. These are Weller. These are $80. These will literally last through years of making cables every day.
Yep.
So,
yeah, those are great. I've actually got those at my other lab.
Yeah, these are great, and they're really comfortable, especially if you're making cables all day.
Yep.
But yeah,
absolutely.
Things like those $20 ones, like I noticed at Kesel, like those technicians were just breaking shit left and right. But a lot of it is because you're trying to cut things that are too big.
Yeah, if you try to cut a paper clip or something that's steel with your $80 cutters, your $80 cutters go to $0 value in a single cut, just like one, like, oh, I'm just going to cut this steel thing really quick, like a, you know, whatever it is. Maybe it's a spring that's inside of some box somewhere. I'm just going to clip that really quick. No, you have different cutters to cut steel. That all of these little cutters right here are intended for copper. That's it. They're intended for wires, and they're precise. They're razor sharp, but they're designed for soft stuff. That's about it.
Hey, Carlos, we got 2 questions if you got a chance.
Yeah, let me check that out. Go ahead.
Curtis Abbott, go ahead. Unmute yourself.
Hey, Carlos. Have you checked out the TS100 as a portable option? I know it's, you said bang good, not so good, but I've seen a lot of good reviews, and it's really cool because you can plug it, you can power it off of Anton Bauer or whatever. It seems like it might be a good option. I don't know if you've had any experience with that or not.
Is that the soldering iron?
Yeah, it's a little pin one, and it runs off at 12. It's like input voltage from 12 to 48 volts or something like that.
No, I haven't tried that one. And like I said earlier, the lower performance soldering irons, you don't really notice their low performance if you're doing fairly coarse work. If you're doing like power cables, like a 4-pin XLR, pretty much anything that generates heat is going to work. If you're doing something like a signal things, like an 8-pin LEMO or something like that, that's when you need a heck of a lot more control and better tips and all those kinds of things. And that's ultimately what drove me to get the more expensive JBC station, is because almost everything that I do is really small and detailed. So I can't speak directly to to that TS100 thing that you're talking about. Is that a butane one right there?
Yeah. So this is really good if there's literally no power anywhere, because you fill the back with butane, but the performance is pretty terrible.
Yeah.
It's really a last resort type of thing, but it's fun to have in your kit.
So there are two kind of performance factors with, let me put this up so you can see my face. Two performance factors with soldering irons, and one of them is the tip. So the shape of the tip and its ability to hold a ball of solder for the solder to actually stick to it. That's kind of performance factor number 1 for me. But the next one is a technical term called thermal recovery. And what that means is the ability for the soldering iron to hold its temperature even when you touch it to something else that's sucking all the heat out of it. So what happens with a cheap soldering iron is it gets super, super hot on the other end of it. And as soon as you touch it to something, all of that heat starts to spread out. The temperature of the tip drops rapidly, and it takes the soldering iron a long time to figure out, oh, look, the temperature went down at the tip. I'm going to go ahead and give it some more energy. And then, that the temperature comes back up. But by the time the temperature goes back up, the solder has melted for a split second, and then your soldering tip is just stuck to the soldering joint because it cooled off really fast, and you have to wait for it to melt again and things like that. Well, by then you're still dumping heat in there, not enough to melt the solder, but you're dumping enough heat in there to melt all the insulation around it and make a big mess of everything. And things start to get kind of gooey. So that's the higher performance soldering irons have a temperature sensor right at the very tip of it. And the instant that temperature starts to go down, it starts to put energy back into it, and it keeps that solder joint melted. And the end result is that it takes less time to make a solder joint. And when you're doing wires, you really want to be able to get the solder joint created as fast as you possibly can, so that the insulation on the wire and the heat shrink and all the other stuff that you have around it doesn't melt and shrink and all that kind of stuff too quickly. So that's one of the frustrations that you'll find with the butane ones that I've used. It's like a sledgehammer of heat. So it just throws an enormous amount of heat into something. And if you're doing a fairly big wire, some 12 gauge wires, and you're going to put some heat shrink over it, you can get it done and get on with the day. But I had a butane one, and it was like my emergency only solution. And then I had my normal soldering station if there's something that I actually wanted, that I cared about, if that makes any sense.
Sure. Hey, Carlos, we got another question.
Yeah, go.
Chris Bolton, go ahead.
Hey, man. You want to talk a bit about the differences when it comes to heat and the tip size?
Yes, the tip size is directly proportional to the amount of heat that will go into the joint over a given amount of time. So I don't think that this camera is going to focus all that closely, but let me show you a couple of different versions. Is that thing hot? So here's kind of a nice thing about I'm just guessing that I'm in frame right now.
Yeah.
So these guys, you can just pull out the tip and drop in another one, which is awesome. So this one, I doubt it's focused very well, but this one is it's like a razor blade tip that can get into really, really tiny spaces. But since there's no surface area on that tip, it's really, really thin. It doesn't transfer heat from the tip to the joint very well. And that's really good when you're working on something where you don't need a whole lot of heat. But if I'm gonna do a big, wire, I'm gonna do a couple of 10 gauge wires together. This is the last thing that I want. The next one that I would want would be something like this. This is like a giant flat chisel tip. And this one can dump enormous amounts of heat into the joint all at one time. So I think I have a total of like 6 or 7 that I use normally. I made this little stand. I machined it, of course. So I've got all these different sizes and shapes to kind of do my regular work, and I'm constantly changing these things. Even on my older Weller that I showed you a few minutes ago, on that one I have probably 7 or 8 different tips that I would kind of go back and forth, and the physical size of the tip is directly related to how big the solder joint needs to be. Did that answer your question?
Thanks, buddy.
Rad. All right, back over the shoulder. When it's cold. What does that mean from Chris? What does that mean?
So sorry, I was doing something else. What was that?
Oh, I was there's a comment says when it's cold from you.
Oh, just when you're pulling out the tip of the soldering iron. It's just like, yeah, just make sure that thing's cold when you touch it.
Oh yeah, so just so you know, I flip this around. This one actually has a tip changer, so you can stick it in this thing and you pull it out, and then you have another one that would be sitting there. So you kind of pick this one up and push it in place.
Oh, fancy. Man, that's nice.
So yeah, it's really pretty quick. So if I was still on set, I'm a little bit of a technology geek in general, but if I was still on set, I would probably still buy that nicer soldering setup, because every time I had to solder something on set, it was almost always a rush, and it was really quick, and it was consequential if I made a mistake or took extra time. And one of the things that the nicer soldering equipment gives you is it's faster. You make fewer mistakes, it's easier to do, there's less frustration, and you can get through the job quicker. And for me, that and all of us are working in a time-sensitive environment, so time is money, which is why like all of the tools that I get are generally I don't make the decision based on money. I make the decision based on how quickly will that tool allow me to get the job done, and how reliable is that particular tool. So let's see if there's any. So here's some other. These are like little supplies that I have. This is silicon sheeting that I got. You get this, I think it's like 12 inch by 12 inch from McMaster Carr. It can deal with an enormous amount of heat. So when you need to solder on something, if you're going to solder a piece, you can put this down on any surface and it protects the surface and it won't melt anything. So I always keep this stuff in my kit, which is it saves you, especially if you want to be soldering on your cart and you don't want to get flux everywhere. That's the great thing. But speaking of flux, that would probably be like, in addition to a soldering station, which you kind of have to have, this is a tube of sticky flux. These things also come in like a pin form like this. They come in little tubs and all those kinds of things. And what the flux does, it's a chemical that kind of a goopy or watery chemical, depending on how you buy it. I prefer this is kind of a gel, kind of they call it tacky flux. And what that does, it performs an incredibly important role in the process of soldering, and that's broken down into two things. The first thing that it does is when it gets up to a certain temperature, it turns acidic and it eats away all of the impurities that are on, whatever you're trying to solder, the copper wire or a pad on a circuit board or whatever that might be. The copper oxidizes really, really fast, and it takes on a bunch of impurities during that oxidation process, and solder will not stick to anything but absolutely pure copper. So what the flux does is when it gets up to that certain temperature, it kind of turns into an acid, but only for a brief moment. It eats away all of those oxidation, all of the oxidation layer, and then it has at that point it's shielded from the oxygen because it has this chemical film on top of it. So the copper becomes very, very clean for just a split second. And the second role that the flux does for you is that it allows the thermal transfer from the tip of the soldering iron into the joint, and it facilitates that. It makes the joint heat up something like 100 times faster, somewhere in that range, and that gets the joint really hot really fast. The solder melts, and then you can pull that soldering iron away before anything else gets hot and melted down. So soldering without flux is far more difficult than with it. So if you're doing two wires, you can just dip each one of the wires in the flux and then put it together. Now, some of you might know that in a typical roll of solder, inside of this, there is flux inside of there, which is kind of helpful, but it's generally not enough to transfer the heat as fast as if you coat the whole joint with some sort of a flux liquid from a pen or from a syringe, or there's a couple of different ways that in the tub or whatever.
Hey, Carlos.
So, yeah, go.
Melissa has a direct question about this right now.
Yeah, go.
Yeah, what type of flux, as far as activation goes, do you typically use? Because I just ordered some mildly activated, and I just want to make sure that that's the better of versus non-activated.
My favorite is this. It's made by Chip Quick. It's called a no clean Tachyflux, and the no clean means that the residue that it still leaves a residue, kind of a goopy residue, but it's not acidic, so it won't eat up your, whatever it is over time. And it's like a really sticky gel. It's kind of like a toothpaste consistency. So it wherever you put it, it kind of stays there. A lot of fluxes it's more like a fluid. It's almost like an alcohol kind of consistency, and those just kind of run off. And so I'm not entirely sure, kind of what the activation parameters are on this one, but I've been using it for years, and I've used probably a dozen others, like in a practical sense, not analyzing them at a chemical level, but just how easy are they to work with. And this Chip Quick has worked really well. The nice thing about this Chip Quick is that you can buy them from DigiKey in these tiny little like single-use tubes, and you buy those in 5-packs that are completely sealed. So when you open one up, you can use it for a couple of days and it's eventually going to dry out, but then you have 4 completely sealed tubes that you can use 6 months or a year later, and they'll still work just fine. So it's the way they package it up makes it really, really easy to keep it with you and not make a mess inside of your kit. However you carry your stuff. The ones that come in tubs and tubes, like if the lid comes off of one of those things, or it opens up inside of your kit, all of your stuff coated in flux is a really bad day. It is just awful, awful stuff. So those little tubes that Chip Quick makes are actually pretty good.
Hey, Carlos, what was the name of that orange mat, the 12 by 12 material you got right there?
This one, this orange stuff is silicon.
Okay.
And let's see.
Everyone's interested in like a product list after we're done with this, just to like.
Oh yeah, sure.
The tools and.
Yeah.
Where to find it, etc.
Here's another soldering related thing. This is a tip tinner. So this cleans the tip, and it kind of preps the tip so that solder will actually stick to it. And keep in mind that this is all just kind of basic stuff. I mean, I think an official soldering class could go on for hours and hours, so we can kind of move on kind of whenever, but keeping the tips clean is important. Which, this is a brass tip cleaner. This is like kind of a brass mesh, and you would take the tip and kind of drag it in there gently. If you kind of jam it in there like that, it's going to mess up your tips. So all you want to do is get some of that stuff off of there, and you can do a little bit of the tip tenor if you needed to, and it should be perfectly shiny, like a mirror shine on the end of the tip.
Yeah, Chase Abrams has a question. Chase, go ahead.
Hey, I was just curious, I did my whole rig with, 4-pin XLR, and it was pretty easy. I went a little thinner than the default tip with my Weller. My Weller doesn't have a digital readout, and that's a pain in the ass as well. What would you recommend? What kind of tips for soldering, LEMO connectors and smaller connectors? I was looking online a while ago, and they showed me something like forceps, where you kind of have these pincers that heat up the pin, and then it kind of melts the solder together with the wire. I mean, just what kind of tricks would you implement when soldering these tiny little connectors?
The limitation with the tiny connectors, or with the tiny connectors, you need the really fine tips, and the soldering station that you own is what's going to determine what tips are available. So Weller makes, there's 3 or 4 different styles of Weller tips. They're not all compatible, like the one that I showed you up here, the super common WES 51. There's only a handful of tip styles that are available for that. And there's small and big and all that kind of stuff. I've had the best luck with kind of like a really small chisel tip. It looks like a tiny little screwdriver. But honestly, the limitations of the tip availability for a soldering station like that was a huge part of what pushed me to buy something like this, which has hundreds of tips available for every imaginable thing, and there's an enormous amount of control over how that works. So not having the digital readout on the Wellers, I don't think that's much of a limitation that much, because that thing responds so slowly that you still don't know what's happening at the tip anyway. But which soldering station do you have? Do you have one of those, the WES 51 like I was showing you earlier?
I'd have to go to the garage, but it's the red one. It's like the lower model than the one you have.
Oh, right. Yeah. Those, the tip availability for those is really limited. Those ones are intended kind of like they're at that like hobby level. And so they've only got a handful of different tips available. And that's what you'll see. Like as the price of the soldering system goes up, usually that goes along with having more variety, more accessibility to different tips and styles of tips.
So if I may, let's just say, in an alternate universe, or 2 weeks from now, I buy this JSB. What just an example, what tip would you use for a LEMO connector? Like, what's your easiest method of doing this? I'm just curious, just because it seems like a total pain in the ass. for
LEMO connectors in particular?
Yeah. Yeah.
Oh, yeah.
This very thin. Yeah.
This was a conversation I had with Jamie yesterday, and my general answer is that it's I might be able to come up with some tips, and that might be on a different day, but soldering LEMO connectors never gets easy, and it's always fiddly, it's always difficult, and it's always a kind of a case-by-case basis depending on the exact connector and the exact wire that you've got, and whether or not it's something that really needs heat shrink on every single connection and all that kind of stuff. But I've soldered millions and millions of joints, and I avoid LEMOs if I can, because they're difficult. I don't know. There's no easy answer to that one, because it's just one of those things. It's hard to. It sounds like, hey, I got this piano. How do I play it? It's like, well, it's hard. It's always going to be hard, because no matter how good you are at playing the piano, there's always going to be something more advanced, and you're going to try to be learning that as well. And LEMOs kind of represent
What about in our world where it's like 2-pin, 3-pin, 4-pin though, primarily?
Well, certainly 2-pin and 3-pin are the easiest of the bunch. And so if you're just trying to do, power cables and all that kind of stuff, I don't use forceps or anything exotic. It's just, I think probably one of the most important things is just being able to hold stuff still. And let me see if I can pull out my trusty pan of ice. There's a lot of different ways to hold stuff, but these little vices are cheap, and if you have 2 of them, that's fine. The little alligator clip things are very frustrating for me, but I still use them every once in a while. But physically holding things still, and so you have one hand for the solder and one hand for the soldering iron, makes things a lot easier. And you will also don't pretend the wires before I put them into the solder cups, because usually what happens if you have a couple of wires sticking out and you pre-tin the wires, then the bulge of the solder won't allow it to slip all the way down into the solder cup, and it kind of becomes a bit of a mess. So I'll twist the wires together as much as I can. I'll put a little bit of flux on the connector directly on the solder cup itself, and if you get the flux in these syringes, this one is connected to a pneumatic dispenser, but you can just push on it like a normal syringe, and I've got this really tiny needle, so you can put a tiny little dab of flux right inside the solder cups, all of them, and a tiny little dab on the wire itself. And if you've got everything like in a little kind of a clamp setup like that to where it's stable, now you have 2 hands available, one of them for the soldering iron and one of them for the solder itself. And I don't usually go at it with the solder and the soldering iron at the same time. I'll usually put a dab of solder on the tip of the soldering iron, just a tiny little bubble. And because both sides already have, both sides of the joint already have flux applied to it, just that as soon as you dabble that solder ball right on there, which is already melted, it'll almost instantly flow into the joint, and it doesn't take very much heat to do it. So if you have like heat shrink, like a tiny piece of heat shrink that is on that tiny little wire, it won't get hot enough to melt the heat shrink. It'll just kind of slide right on. And that's
great. Wow.
Usually goes pretty quick. But none of that would be possible without some sort of flux on each side of the joint.
That was the most important thing you'll learn today, right there, everybody.
Yeah, if you just have like a dry joint, for example, your only real option is to take the soldering iron and you would hold it onto the joint. You have to wait for it to get hot enough to start melting the solder, and then you feed the solder in with your other hand. And by the time that happens, the insulation on the wire has started to melt, and if it's like a PVC insulation, it'll shrink. So, you might have had a tiny bit of wire sticking out. Now, all of a sudden, the insulation is shrinking. You've got a whole bunch of wire sticking out. And if you had heat shrink on that joint that's fairly close by, the heat shrink will have already shrunk. And the frustration goes through the roof.
Every time.
Every single time. So a little bit of the flux on there, it transfers the heat so quickly, cleans the joint, flows the solder so quickly that it doesn't overheat anything, and you just kind of move on.
We have a question from Chris Bolton.
Yeah, go ahead, Chris Bolton.
I think you just covered it, but I was just gonna say lots of heat and quick heat transfer is key to get those solder points on there without melting your fingers.
Yeah, that's exactly. If it's melting your fingers, you're doing it wrong. Because if it's melting your fingers, you're also melting the insulation, and you're shrinking the heat shrink and all of those other kinds of things. So you should have the cadence of the whole process down to where the amount of time that you have that soldering iron touching the soldering joint should only be enough to melt that solder and get the heck out of there. So you don't like hold it on there and like wait and wait and wait. If you've done it correctly, that soldering iron should be in and out before everything around it just gets so hot that you can't touch it.
Yeah.
So a little bit warm on your fingers is like, okay, that's no big deal. But yeah, if you burn your fingers, you're in trouble.
I did have a question about when you store your tips. Do you keep solder on the tips, or do you clean them?
I clean them before I put them away. And the The JBC tips, I think I've had those for about 3 years, so each one I bought, the one that I just showed you, had those for about 3 years. They're used constantly every day, and I haven't worn any of them out. The ones on the Weller, I would buy new tips about once a month. So I can't remember exactly how much each one of those things were, but I'd say probably over the course of 3 years, I've probably saved the difference in money between those stations by never replacing the JBC tips, where I had to replace the Wellers all the time. And even when I was replacing the Wellers, because the choice is limited, I was always getting the tip I didn't really like anyway. So anyway,
Cool.
Another thing that's probably worth pointing out is this is a stereo microscope. I don't expect anybody to keep one of these things on their cart, but one of the things that I kind of keep in a field kit is a high quality loop that's used for like inspecting 35 millimeter negatives and things like that. You know, a high quality, you know, kind of single glass optic, because when you finish with your you know, soldering your thing together, if it's relatively small, like a 2-pin LEMO, you can look at it with your bare eye and be like, yeah, that's really great. And as soon as you get it up under a microscope or one of the a loop, there's a lot of times you'll discover there's like one tiny little wire that's really difficult to see, that's just kind of hanging out in the breeze, and that's the wire that's going to short something out if it's not already touching something else. So having some sort of magnification, you can also get one of these cheap USB microscopes. These things are pretty darn small. Like, is my video still up, by the way?
Yeah.
Okay, good. So yeah, these little guys for a lot of applications are kind of crappy, but these things are more than good enough to figure out, after you've soldered something together, do I have like one little wisp of wire that's kind of, you know, hanging out, that's going to screw up my soldering job. And, you know, for those that use like really nice wires like a Mogami, what makes a Mogami cable super, super pliable and flexible is that each individual strand is extremely small, and you cannot see it with your eyes. So you could have 1, 2, or 3 strands that kind of got pushed out of a solder cup, and they're right next to another pin, you know, positive to negative, and it'll create a direct short, and you won't be able to see it with your eyes. It'll look just fine with your eyeballs until you put the heat shrink over it and you seal it all up and you plug it in, and you know, something, you know, blows a breaker or whatever, blows a fuse. A little magnifier is a good thing to have. So is there any other, what else have I missed, like with soldering and tools and all that kind of, wire strippers.
I was gonna say, Carlos, like if before we're done, if you can just do a quick little demo, so, you know, just to show people how it goes, that'd be awesome.
Oh, sure. So I've got a whole bunch of fancy wire strippers, but I'd say I probably use these more often than any of the others. These are like regular kind of run of the mill at probably $15 or $20. They have their limitations. Typically, these mechanical strippers will, if you're trying to strip wire with that stranded, you'll end up getting a couple of strands with this. If you're making power cables, the last thing you want to do is break some of the strands out. So for that one, for the really delicate stuff, I use one of these guys. It's a strange little thing, but this is called a thermal stripper. And this end of it gets super hot, and you stick the wire in there and it melts the insulation, and you just kind of peel off the insulation. It doesn't actually cut anything. It just melts the insulation away. So this is a way where you can strip any wire and be guaranteed to not pull off a couple of strands in the process. Sometimes that's critical, sometimes that's not. With the Mogami wire and others that are like the really high quality flexible stuff is difficult to strip with the cheap mechanical strippers. I don't have any here, but there are some like fully automatic strippers that they automatically adjust to like whatever size. Those typically don't work with small wires either. Those will work with, you know, 12 gauge, 14 gauge, 16 gauge wire. If you're making fairly big primary power cables, like a 4-pin XLR. But I don't use them very much because most of what I do is the smaller gauges. And does anybody want to, well, I guess we might be able to cover some like wire gauge type stuff a little bit
Yeah,
later.
we should
but,
definitely talk about like recommended wires for like 2-pin, 3-pin, 4-pin cables.
But yeah, I guess after the fact, I can, you know, kind of lay some of this stuff out, and you know, this is kind of what I use. These are some things that other people use. Links to DigiKey for flux and the solder that I like the best, and that kind of thing, if that helps.
Yeah, of course.
Let's see. I think we.
Would you mind?
Oh, go
Would
ahead.
you mind talking about cable, like the recommended cable for making LEMO cable, or like 2-pin, 3-pin, 4-pin, etc.?
Yeah. So depending on I guess the first thing you have to do when you're making any cable is decide what that cable is going to carry. Is it purely for power, or is it for signals? And obviously signals don't carry much current, so that one you're concerned with signal integrity, shielding, all those kinds of things. If it's purely power, if it's just going to power up your monitor or whatever, it's a 2-pin LEMO, like a 4-pin to 2-pin LEMO. At that point, you're worried about current carrying capacity. And this is an interesting one. This is one I didn't you know, when I was growing up, I didn't understand this for a long time. You'd see like a chart and it says this size cable can carry this much current and this one can carry this other amount of current. So say you had a wire and the manufacturer says, yeah, this one can carry 3 amps. It's like, well, what happens if you give it 3.1 amps? Does it immediately vaporize? And the answer is no. And like, well, where did they come up with those ratings? And the ratings for any wire are based on how hot we will allow it to get, and that is generally determined by the jacket that goes around it. So as most of you would intuitively know, wire has resistance, and generally that resistance is so small that you can't just take an ohm meter and put and measure it directly. It's a little bit harder because it's pretty much always below 1 ohm. It's like in the milliohm territory. So if you had like a 20-inch piece of wire, maybe that's 2 or 3 milliohms. That's 2 or 3 thousandths of an ohm, which doesn't sound like a whole heck of a lot of resistance until you start running current through that thing. And what happens with resistance is the same thing that happens when you kind of put your hands together and you go like this. Well, the harder you press your hands, or the less distance there is between them, you rub them together, they get hot. They get hot pretty quick. You know, rug burns. Anytime you rub 2 things together, you rub 2 sticks together, it catches on fire. That's kind of the same thing that happens in a wire. There's some resistance, and the more current you're trying to push through there against that resistance will heat up the wire. And eventually you'll get up to a temperature that starts to soften the jacket that is around them. So if it's PVC, those are really low temperature. And what the manufacturers are doing is they're saying, okay, this is kind of the maximum temperature I can be, and that PVC jacket is still strong enough to be considered safe. And you keep on heating it up and heating it up and heating it up, and eventually it'll look like the wire inside of a toaster. It'll just turn red. All of the insulation will vaporize. And I think I did I think there's a video. Maybe we could link this after the fact that I did of another manufacturer that makes power distribution products. They had some wires inside of the box that were a little bit too small, and the box said that it could handle 10 amps. So I put 10 amps through it, and about 30 seconds later, I could see and smell smoke coming out of the side. I'm like, what the heck is that? And when I finally opened it up, all of the wires had melted themselves together, and it was just a charred mess because the wires were too small for that amount of current.
You should definitely show us that video.
Yeah, it's on YouTube. See if I can.
Oh, yeah.
It's pretty funny. It's, you know,
Did
product A and product B. I'm not going to mention any names.
Yeah. Did anybody have any questions? Looks like Chris found it already.
Oh yeah, if there's anybody can like post that link. So yeah, so the size of the wire is entirely dependent on how much current. The voltage doesn't matter so much than the current, but it doesn't necessarily stop there either, because there's some wires, like if you're right at the limitation of it, say this wire, whatever, is rated for 5 amps. If you actually put 5 amps through it, it's technically safe at that point, but you're still, the voltage going in and the voltage coming out are different. And that voltage drop from one end to the other is what is turned into heat. And in a 12-volt system, you don't have a whole lot of difference between the ideal voltage and the lower voltage where everything just starts to turn itself off. So instead of worrying about the total capacity of that wire and how hot it can get and all that kind of stuff, what concerns me the most is how much voltage drop can I tolerate from one end of the system to the other, like from my battery source or my Meon Life or whatever it is that's providing that thing. How much voltage drop can I tolerate from one end of the system to the other? And on any camera system, for example, if you were able to measure the current right at the terminals of the battery, and then it goes through a distro box and it goes through another thing and a bunch of cables and all that kind of stuff, and ultimately makes it onto the to the camera. On most systems, you'll find that it's dropped about 1.5 volts or so between the battery and the actual camera. And the displays on a camera are always going to show you a lower voltage than what the battery is actually giving you. But how does that impact you in real life? Here's where it gets ugly, and I have a nasty experience with this. Doing a helicopter job. What's that?
Techno cranes.
Yeah, techno cranes. And the my worst experience was a helicopter, where the battery comes off with a charger at 17 volts and it kind of stops working at about 11.5 volts, and that 11.5 volts is roughly where the camera kind of shuts itself down. But if I've got 1.5 volts drop between the battery and the camera, because my wiring and connectors have a whole lot of resistance, now that means that when the battery's at 13 volts, the camera thinks that it's 11.5 volts and it's already turned off. So now the battery still has 40% of its capacity left over, and the camera is already shut off because of all of the resistance in between. And that's exactly what happened to me on a helicopter job. The camera was up on the nose of the helicopter. Initially, I was going to be in the front seat, and then they said, "Oh no, you want to be in the back seat because we got to do the operator panel in the front and all that stuff." So I kept on extending the cables, kind of continuing on. This was a while back, and I tested everything, and it was a golden hour. We had like this narrow tragic hour type of a window to get the thing, and we were sitting around all day. It's like, yeah, it works. I've got tons of extra batteries and they're all charged up and all that. What I didn't realize is that I was getting about 3 or 3.5 volts of drop between the camera and where the batteries were because of all of the resistance in the cables. And so we get up in the air, and like as soon as the helicopter took off, I get a battery warning light. I'm like, oh, okay, whatever. I change the battery, I put on the next one. And about 5 minutes later, the battery warning light turns on. I'm like, oh my God, like we've got about an hour-long flight here, and I've got enough batteries now, based on them lasting 5 minutes a piece. Like the batteries still have a ton of power in there, but it can't get to the camera because of all the resistance in the wires. So it's an example of if everything else was exactly the same, except that I had humongous cables going to the camera, the voltage drop would be a lot less, and the batteries would last the 1.5 hours that I was expecting them to last. So that's kind of what I tend to think of when I'm trying to figure out how big the wires need to be. So if you're going to make a tiny little cable that's, say, a P-tap to 2-pin LEMO that's going to power a super low current monitor, and it's 12 inches long, really your concern there is probably how flexible is the cable, how easy is it to work with, and all that kind of stuff, because the drop over with a low current device over a very short distance isn't going to be enough to care about. But if you're making a cable that needs to go from a VCLX to an ARRI LF, well, now your cable is very, very important, because the LF, I can't remember how many amps that thing pulls, but it's like, I think it's 10,000 amps or 50,000 amps or something. Obviously kidding there a little bit, but like some of those cameras, they pull an enormous amount of power. The more current that the system draws, the more voltage drop you get in the cable. And that's the important part. If you had a cable that was 100 feet long and you plugged in 14-volt battery on one side and you took a voltmeter and you measured the other side, it would say 14 volts. It'd be nothing. As soon as you start putting a load on that thing, that voltage is going to go down, down, down. You're going to start eating up that voltage as the current starts flowing through, and that kind of gets us to Ohm's law.
Would you mind going over like using a meter on set to check and see like the battery, like let's say for example the battery's outputting a certain voltage, and then you plug in a 30-foot 4-pin or 3-pin extension cable? What would be your process to check and see like how much you're losing over that cable?
You know what? Let me see if I can, how quickly I can come up with something over here. You know, a lot of people will measure the voltage at like before everything is actually loaded up, and you're always going to get the same voltage on both ends if there's no load on the system. So let's see if I can do this quickly.
We should talk about inrush since you're set up after this.
Oh yeah, that's a good one. Let me see if I can. There's a kind of a set meter. This is the exact same thing, but kind of intended for bench. This one just runs on AC. This one's obviously, you know, can run on battery power. Definitely don't recommend that kind of thing for set, and something like this is a super reliable, you know, Fluke 87. It's been around forever.
Hey, Carlos, Chris Bolton has a question real quick.
Yeah, go ahead.
Maybe now it's not the right time for this question, but do you want to also mention the reasons why some things use higher voltages instead of using like 12 volt, like why they use 24 volt?
Yeah, the voltage budget. All right, so maybe if I can do two things at once, I will try that. Let's see. Yeah, this may take a little bit longer to set up than we have time for right now. But yeah, what's the difference or the benefit of 24 volts, you know, versus 12 volts? And generally speaking, if you have a system that has fixed power, you need 100 watts, for example. The wattage is a term for power, and that is derived from multiplying the voltage times the current. So if you have 12 volts at 10 amps, that's 120 watts. If you double the voltage and you still only want, you only need the 100 watts, then the current is cut in half. And the size of the cable necessary for a particular task is not determined by voltage, it's determined by current. So if you double the voltage from 12 to 24, the current requirement for the same amount of power is cut in half. Therefore, the size of the cable requirement is also cut in half. And that's why you look at like power generation on a large scale that has to travel hundreds and hundreds of miles. The giant towers, those operate at about 500,000 volts. You know, extremely high voltage, because they need to get the current down to the point where the resistance in the wire is less of a factor to be able to go hundreds of miles to get to its destination. And then as it gets closer and closer to the destination on a transmission system, it gets stepped down from 500,000 to 200,000 to 100,000 to 18,000 to, you know, whatever all the intermediate voltages are, until it finally gets to your house and you're using 120 volts. But if you tried to you know, transmit 120 volts, like it's like a stinger on set, and you plug in a 2,000 watt light at the end of a 400-foot stinger, that light's only going to be getting 70 volts at the other end of it. So that's kind of does that make sense? Kind of why you would want the higher voltage and how that helps? Use lower current requirements. The cables get smaller. The heat generated is lower. The impact of resistance through all of the connections is smaller. And if you have a converter system that can take, say, from say 18 to 36 volts, which is pretty common, and you have a battery that say starts at 28 volts and goes down to 22 volts, you'll be able to get the entire use of that battery while the converter's spitting out 15 volts or whatever it is that you want for your primary equipment. Because at that point, your equipment would only see what comes out of the converter, and which be constant, and the voltage converter would be able to fit within the range, the voltage range that your battery is able to give you. So you're able to take that battery from 100% charge to 0% without having to deal with the voltage drop in the cables. Not sure if that makes a whole heck of a lot of sense without visuals, but